Okay, it's lecture 25, the last lecture of our semester. Okay, as I told you before, today will be the last lecture, and next Monday at 9 o'clock we will have the final examination in this classroom. And you know, the final examination will be quite similar to that of midterm examination. So please prepare in a similar way. So we have learned a lot of analytic expressions for MOS system especially. So please concentrate on the second half of our entire semester. So the first part will not be covered extensively. Okay, so in lecture 25 we will try to cover as many as possible, as much as possible we can cover in this lecture contents, but let me just try. So I just bring this ID expression simpler form here just for reminder, and as you can see we have some terms corresponding to the linear function of a VDS and also square function or parabolic function of a VDS, and also here we have another one corresponding to the power of 1.5. So yes, some complication comes here. However, for example, in the previous lecture we have made a regional approximation. Yes, in this linear or trimode reason, then we can consider just small VDS values by definition, and in this case we can make a Taylor expansion only up to first order. So that was the case, and you can see that the IV characteristics we can calculate out of our simplified expressions is a little bit off from the more rigorous one. It was because we made an assumption that surface potential is just fixed to 2 times phi b, which is slightly underestimated the surface potential, because our inversion layer itself consumes a small portion of electrostatic potential. So in order to have a fully working in order to have a sufficiently high electron density, actually we must increase our surface potential a little bit further than just 2 times phi b. However, that effect was not considered in our present expression. That's the reason why we have a slight up and our underestimation of our threshold voltages. So by just make a simple calibration, then we can have a much better one. And you can see that up to now in our previous course we made an assumption that VDS is quite small or almost equal to 0. So the thing we have studied up to now is just limited to this way. So today we will talk about certain behavior corresponding to here beyond quite a small VDS value, and clearly we can see that beyond a certain level then the current is saturated, and that will be quickly covered in our lecture today. Okay, so I hope that already you know the answers, but let me just remind you how can you treat it in a unified manner. Okay, so in this parabolic reason, so instead of making the Taylor expansion only up to the first order, so now instead of this one, just to keep the second order. So if we consider the second order quantities, then obviously this term, the previously neglected term. So square of VDS comes in. Yes, that is the dominant one. But please have a look at this part. Another important term comes from this one corresponding to 1.5 originally, and you can see that this was the linear, and this is corresponding to the second order term. So when you have a look at it, then you can see that. So compared with the previous one, now we have a newly added component, and this newly added component, of course, together with this second order term, will give you this kind of coefficient. So please have a look at this one. So COX is common for our two terms, so we don't have to worry about COX. Then if we just consider the remaining terms, then let me just write down once again VGS minus VT threshold voltage. I'm just writing down in this way, and VDS, yes, you know it. And the second term is corresponding to half of VDS square. Yes, we know it. But please have a look at this expression, equation 3.25. Can you identify this term as this blue one? Actually, it is a little bit difficult because in front of our second order term VDS, here we have a term with a square bracket, and it is having the form of 1 plus something. So we can see that, yes, if they means that these two terms, COX and square root of something, both of them are positive quantities, so we can say that at least this quantity is positive and higher than 1. So in this case, if we have just number 1 instead of this complicated expression, then it is reduced to your junior level expressions. You have seen it before in your microelectronics course or something like that. So that was the expression. But after spending quite a lot of time on this MOS structure, now you find that this coefficient is a little bit modified from our previous simple expression. So let me just consider why we have this kind of behavior. But before talking about the long history about or long discussion about this kind of thing, so please think about this term once again. Here we have one term, added term. That is the main reason why we have just half, but we have a half times something. Then where do we have this term? This term is also originated from, of course, this term. And if you come back to its original form, then where can you find the term related with this one? Yes, your modification to your simple expression comes from this term. And what is the physical origin of this component? This is corresponding to the depletion charge related term. So you have to understand this is the first one related with our just normal inversion charge, but that is more related with our depletion charges. So maybe you understand this kind of behavior is related with something with a substrate. Okay, so now this term, the newly added term, is denoted as M. So well, this is more or less a universal way to represent this number. Yes, here we have a M, and this M is simply given as as shown in the previous one, it is given as just number 1 plus something. Yes, what is it? So you can understand this is so here you have a C ox, and this is a unit list or dimensionless quantity. It means that this upper part is also corresponding to certain capacitance per unit area, because this lower part is corresponding to the oxide capacitance, and it has the unit of farad per square centimeter, so it will have the same dimension. So division by these two terms, between these two terms will give us just a unitless dimensionless number 1 or something. And you can see that this is just corresponding to this quantity is corresponding to the maximum depletion width, which can be obtained when we have the surface bending surface potential of 2 times phi b. So this is the WDM, and please have a look at this upper part once again. It can be regarded as this point. So WD 1 over WDM and epsilon silicon. Please try to estimate or calculate this expression once again. Epsilon silicon and inverse of WDM can be just written as, yes, here we have a silicon epsilon phi b, and here we have q times and a. Then of course here we have epsilon and epsilon, so that will give us just epsilon silicon here, and you can easily identify that the upper part shown here. So let me just slow down. This term can be expressed as just this one: silicon permittivity divided by width over our depletion layer. So what is it? This is corresponding to the per area capacitance of our depletion layer. So simply speaking, now you can identify this n factor is corresponding to the 1 plus the ratio between two aerial capacitances. One capacitance is related with our depletion layer, and other one is oxide layer. So you can see here. So I just follow the notation of our textbook, Professor Tower 1. So, but anyway, you can see that this m is corresponding to 1 plus ratio of our two different terms. So please try to estimate the behavior of our m factor. How can we get its minimum value? Its minimum value would be, of course, 1. In order to get this minimum value, what we can try is have depletion charge or depletion capacitance much smaller than oxide capacitance. Then how can you realize this extremely small, relatively small depletion charge? The simple way is to make very wide depletion layer. If you have a very wide depletion layer, then this CDM is just proportional to epsilon silicon and inversely proportional to the WDM. If you have a very wide depletion layer, then you can maintain your depletion layer quite small. Then how can you increase the width of your depletion layer? You know the trick. So if you just increase doping density, then your depletion width narrow down. So simply, if you wanted to have this M value close to 1, then the best way would be just to have relatively low NA value. If you have a low NA value, then your CDM, so maximum depletion charge capacitance, can be much lower than your COX. Then you will have the value quite close to 1. Okay, so if you have this kind of approach, then what will happen to your system? Okay, now your device shows quite good, as we will see later, quite good relation between your gate voltage and surface potential. So your surface potential can be well controlled by your gate voltage. That is a good thing. However, if you introduce this kind of quite small doping density, that is directly related with the reduction of your threshold voltage. So as I told you in our last lecture, so we have to have certain reasonable value of a threshold voltage. So if you wanted to make just a good transistor, then you have some tendency to reduce it to down to number 1. But if you try to this way, then that will be just to change over your threshold voltage. Then how can you do that? In order to maintain a certain reasonable value of a threshold voltage, it means that your NA value is more or less fixed or given to you. Then given value of NA value, it means that your CDM value is also automatically given. So your M factor cannot be quite close to 1, but unfortunately your value will be higher than number 1. So practically in a former times, people, when they working with this planar MOSFET case, they had to make some compromise between their M values and actual threshold voltage adjustment. So they thought that, well, maybe 1.1 or 1.4 would be an acceptable value for our M values. It means that your depletion capacitance is just 1/10 of oxide capacitance, or 1/4 or about 40% of your oxide capacitance. That was the available value you can have. So maybe some of you feel that why we have to care about this M value quite significantly. So that will be quite obvious after some minutes later. But this M value is directly related with the subthreshold slope. So once you understand this M is directly related to the subthreshold slope, then you wanted to keep it as low as possible. So please go to this one. So of course we have the opposite direction to reduce M values. Can you imagine? So up to now I have explained the way to reduce this CDM value as much as possible. So however, we have to try another value, another way. Another way is shown here. If we can increase oxide capacitance, then that is also directly affecting to reduce our M value. So that is actually the driving force for introducing multi-gate structure. So in order to have steep subthreshold slope, of course we can try to reduce NA value, but that is not a way we have to follow. The other way is try to include more gates and effectively increase this oxide capacitance further and further, and that will give you eventually the value quite close to number 1. So I want to say that nowadays we can maintain the M value quite close to 1. So if you are working with the state-of-the-art device, maybe to you it is not that surprising, the value close to 60 millivolt per decade, but it was not achievable in our planar MOSFET case. When you have a look at the previous papers of about 20 years ago, then you can easily see that even the manufactured devices shows the subthreshold slope close to 80 millivolt per decade or even higher value. Okay. So also I wanted to recommend you to think about your own device. Maybe some of you have your own device, and when you characterize your system or your device as a logic application, then what is my subthreshold slope? So since the mass production silicon technology can provide us the ideal value 60 millivolt per decade, the competing or alternative devices should be able to provide such a kind of behavior also. Okay, so well, here I have one interesting thing here. Then in our previous example, we have used quite a low Na density. It was just 10 to the 17 per our Na value, and it was just about 1.1. So why we had such a low value for our M value? Because here we have used quite a low Na value, but instead of that, what we had was this behavior. So can you see? So in this case, our threshold voltage linearly extracted from our IV input characteristics is as low as just 0.3 volt. It means that 0.3 volt is not acceptable for conventional logic technology. If we are working with, for example, 2.5 volt as a VDD value. So nowadays, of course, our VDD value is just 0.5. So in this case, if your threshold voltage is 0.3 volt, then I would say that, oh, your threshold voltage is too high. There is no sufficient room for your device to be highly overdriven. So instead of that, I would like to suggest to you the values more close to number 0.2 or something like that, just 1/3 or a quarter of this VDD value. However, please note that the example we have considered up to now is just taken from quite old technology. At the time, the VDD value was 2.5 or even higher, 5 volt. So in this case, this kind of such a low VT is not acceptable. Then how can you increase, 4 more times, how can you increase your threshold voltage? Then you have to introduce more doping into your system. Then, well, let's think a little bit further, the case where you introduce higher doping density. So think about the effect of introducing higher doping density in your device. If you introduce higher doping, then of course your threshold voltage will be increased, so you will have this kind of behavior. However, you have also one effect I told you before. The there are two major components to determine your effective mobility, and one of them was doping density. If you intentionally increase your doping density, then your mobility value is drastically reduced by this higher doping density. So so it is not that good approach. However, then maybe you can give me another alternative way. Well, we have another knob to control threshold voltage. So please have a look at the definition of our threshold voltage as shown as equation 3.24. When you have a look at this one, what we are doing currently is just changing NA values to increase threshold voltage. For example, if you just increase your NA values by factor of 100, then wow, the contribution from this component will be just increased by factor of 10. So that is main factor we can consider. Of course, if you increase also threshold doping density, then this is also corresponding to the log of NA value. However, since we just take log of NA value, its increment is not that drastic, so it is not a main factor. Well, so anyhow, if we increase the dopant density NA, then we can increase our threshold voltage. But when you have a look at this equation 3.24, you can identify more direct term which affect the threshold voltage. Can you point out the more direct term to control this threshold voltage? So you can easily understand this one. The flat band voltage is directly related to the threshold voltage. If we can increase this flat band voltage or increase or decrease anyway, then depending on our change of flat band voltage, then we can also directly control threshold voltage. Wow, that is the best way we can do. But what at former times, why we have not tried it this way? At the time, due to the limitation of our technology, previously we did not actually use this metal gate. Previously, at the initial introduction of this MOS technology, metal was actually used as the gate. So, but unfortunately, the problem was we had no choice for metal. There was only one representative way to fabricate this gate metal, and the choice was just aluminum. So since aluminum is the given metal and since it has a given work function, so we had no knob to control the flat band voltage. Of course, this flat band voltage is obtained from two different factors: metal work function and another one is doping density. So however, this is just a given number, and now let's go to the next stage. In the next age, so instead of using this metal, we have used polycrystalline silicon as a metal instead of a metal gate. In this case, polysilicon, in order to have it as a gate material, then anyhow we have to increase our dopant density as much as possible. Otherwise, gate itself contains a lot of resistive component, so we cannot use it as gate one. So there was no chance for us to control this dopant density. So the rule was just to increase our polysilicon gate doping density as high as possible. But now we are in the third age, and now we have a metal gate once again, and fortunately now we have some capabilities to adjust the work function of our gate metal. So nowadays, previously, in order to control this threshold voltage, the main player was doping density of our substrate. But now, instead of this substrate, now we can control gate work function, and relatively the role of our dopant density is reduced. That is directly related with the relative reduction of our doping density. We can maintain relatively low doping density, and that is critically related with relatively high effective mobility, because as I told you before again and again, mobility is highly restricted by the doping density. So now we have a certain knob to free our effective mobility from doping restricted or doping limited value. Okay. So however, the textbook shows just all the time story, so we just feel that work function, gate work function is not adjustable, so we just rely on changing the doping density, substrate doping density, to control the threshold voltage. Okay, so anyway, so I have stressed the importance of this M values, and how can we reduce this M value. This M value was just a ratio between depletion capacitance and oxide capacitance, and it clearly reveals that it is good to have high oxide capacitance at the same time low depletion capacitance. Then what will be the best way to have this value exactly equal to 1? The best way, of course, increasing CO2, it's good, but another way to have the value, M value equal to 1 is just to make it 0. When CDM equal to 0, then it means that exactly we have number 1. So how can you obtain this kind of situation? Seemingly quite unreasonable. I'm just saying that our substrate has no capacitance at all. But please think about the physical origin of capacitance. So in this case we have CDM. It means that if we change this surface potential a little bit, then if we slightly increase this surface potential, then we have additional charges, and additional charges collected across our depletion charge, a depletion layer. And it was possible because here we have quite a thick layer of p-type silicon resin, so we can supply our negative charge or positive charge just to moving holes. These holes can be attracted or just repelled slightly, so they can provide certain capacitance. But now think about this one. There is no hole any further. No hole at all anymore. Then although you change the potential at this point, surface potential, but you have no ability to further provide your holes or reduce the hole density. So if you have this kind of a situation, then your capacitance would be just 0. So please note that once again, the physical origin of our so-called depletion capacitance is our p-type substrate can provide a lot more holes or reduce the hole density across this depletion layer. However, if our substrate, p-type substrate is completely depleted, then this substrate has no ability to further provide holes or just to reduce the density of holes. So maybe we need to overlap. Then let me just explain once again. This is a real practical problem, so it is not just an ideal one. Think about a finite silicon substrate. Up to now, we have assumed that our silicon substrate is quite deep and thick, so the position of our p-type substrate contact is just located at the far away from the surface, and it was taken as infinity. But instead of that, so please think about a certain amount of thickness, finite thickness. For example, typical value can be 20 nanometer or some around a certain 10 nanometer scale. So in this case, depending on the values of your system, so now here we have a gate, and already when we have the equilibrium or zero gate bias condition, then we can make certain condition all over our p-type substrate is depleted. So previously, instead of let's say that instead of this 20 nanometer, let's say that this thickness is 1 micrometer. Then what will happen? So then part of it is depleted and part of it is still neutral. So if you change our potential here, then we can add more holes or reduce the number of holes at this boundary condition. However, instead of this relatively thick structure, so let me consider our structure itself is just as thin as this way. So when we just start our analysis, our p-type substrate is already completely depleted, and here we have holes and here we have no hole at all. Then when you change your potential, what will happen? Then this system has no ability to further provide negative charge or positive charge. So what we can say is, okay, charge state is not changed. So please note that Q equal to CV. So when you change this voltage, if you have meaningful C values, then you will have also increase of your charge across your system or decrease of your charge across your system. However, in this left side figure, which is already completely depleted, then although you change potential voltage at this surface, but you don't have any change in your charge. So what is it? Although you have change B, but this is 0, it means that you don't have any kind of meaningful capacitance C. So simply means that, so please, to some of you, this discussion seems to be too abrupt and too ideal. However, that's real. If we reduce the thickness of our silicon further and further, and if the thickness of our silicon becomes below the depletion thickness of our conventional planar MOSFET, then we can enter into the region called as completely depleted substrate. In this completely depleted substrate, then as I told you before, our depletion capacitance can be maintained as just 0. Wow. Then what will happen? Then it means that now we have just a number close to 0, so m goes to almost identically number 1. Then once again you can ask me this question: is it real? It is too good to be believed, because by just introducing quite a thin silicon substrate means that we can improve our m values ideally. Previously means that 20 years ago, or several decades ago, it was very difficult for us means that engineers, to realize such kind of extremely thin silicon substrate. It was really difficult, and it was only possible by using very expensive so-called SOI wafer. So why it is called as SOI? This is nothing but silicon on insulator. So simply, how can we make a silicon wafer? We just make a silicon ingot and just slice it. So this is relatively cheap process, because we have a bulk silicon and just slice it and polishing the top surface and bottom surface, then that can provide us the usual silicon wafer. However, in this SOI wafer, first of all, we have to have a bulk silicon, and on top of it we introduce a very high quality insulator, and once again on top of it we grow very high quality silicon, which will be eventually used as a channel material. So cost or price of this SOI wafer is way higher than bulk wafer. So there was two different companies or two different trends of technology development. So there was MOS1. After that, they feel that, oh, our performance is now hitting the wall. Then how can we overcome that problem? At that time, two different companies groups are taking two different ways. One way was, okay, I will just keep use this bulk wafer. Although bulk wafer does not give us good enough performance, but anyhow I will try to use it because it's cheap. And there was another approach. So the most representative example was IBM. So maybe you have heard about this company, and they believe that performance is the king. If we can provide good enough semiconductor chip, then although that is quite expensive, but our customer will love it. So they switched to SOI wafer and fabricate very good technology. So please think about the situation. At the time, planar MOSFET always suffer from this limitation. Their M value was not that low as 1. However, by using their silicon on insulator wafer, SOI wafer, although expensive, but IBM fabricate quite good quality, much higher performance devices at that time. So expensive and highly qualified, and it was used very specific cases. What is the specific cases? Like your supercomputer. So they don't care about the price at the time. So they just wanted to have the fastest and most reliable one. So that was the situation, and this one was just to use commodity electronics. For example, your PC. Well, your PC, when your PC is gone, broken, but nobody cares. So you can just buy it again and again. Of course, your children will not be very happy about that situation, but that is not that much expensive. But let's consider supercomputer. Then supercomputer is quite expensive, and even giant company can buy it only once for given time period. So that was situation. However, that was a former situation, and now everybody can make this kind of completely depleted wafer, or not wafer but silicon channel. Now people can make quite well defined silicon layer on top of just the bulk silicon. So they can make it. So let me just explain a little bit further about how they did. Well, sorry, it seems that the system is also stuck. Oh. So the trick they have made fully depleted substrate was first like this. So we wanted to make a quite thin layer, thin silicon layer out of just bulk silicon. So now here we have quite a thick bulk layer, and ideally what we can do is just to make a really thin layer vertically. Then we will love it. So if this is silicon, then we will love it. But unfortunately, that was not the first trial, first technology we did. Instead of this thin layer along this vertical direction, but they were able to make this thin layer along this lateral direction. Please have a look at this one. Instead of silicon and oxide and very thin layer silicon, that is conventional SOI device, SOI vapor, and you can control the thickness. You can just make an order to your wafer company, please give me 20 nanometer thick one or 10 nanometer thick one, so they can make it. However, that is quite expensive. Instead of that, they made it this way. So previously its shape was just a planar wafer. However, by introducing certain etching patterning, so now they can introduce quite thin vertical structure. So typically this is like 5 nanometer or around 10 nanometer. So using this one, of course this is not actually vertically thin, but instead of that, this is horizontally thin. So using this structure, if you have, for example, if you have gate in this part and that part, let's say that this is your gate and this is your gate, then the thickness of your transistor would be just defined as what? Defined as the width of your silicon structure, vertically thin structure. And if you can make it thinner and thinner, then you can make an even thinner silicon channel. And if you control the thickness wider and wider, then you can have wide one. So that was the first thing we have done in our previous years. Previous years means that about 10 years ago we did this kind of technology. So are you with me? So in this case, how can you control this thickness? The thickness was controlled by the ability to make this width. Then how can you make this width? It is all related with lithographical patterning and also etching capability. But nowadays, instead of this technique, so we have also another alternative technique. So starting from certain silicon layer, we just introduce a different material. This one is not silicon, but a little bit different one, very thin, like just a few nanometer. After that, we can grow once again silicon and alternative material and silicon. After that, the key point is this so-called alternative material is just located here, and it can be selectively etched by certain method. Means that after etching this alternative material, then later we will have well-defined silicon and well-defined silicon in this way, because this alternative one can be easily etched out selectively. Then what is the thickness of this silicon channel? Then this will be the thickness of your silicon channel, and also this will be the thickness of your silicon channel. Then please think about this situation. What is the determining factor to define the thickness of your silicon? In this case, the thickness is defined when you grow this silicon layer. Then growing, this growth process can be controlled quite accurately by one layer of atomic layer and another layer of atomic layer. So you have a much better controllability to the thickness. So please think about this one. Previously in this case, you just first make a very wide bulk silicon, and just by etching them all, you define the thickness. So if you have a certain uncertainty in or variation in your etching process, then the definition of your thickness will be changed. However, when you have this growth-based approach, actually this growth itself defines the thickness of your silicon, so that is good for defining well-controlled silicon substrate. So why we are spending so much time on this topic? Because this M is so important. So as I told you before, this M is directly related to your subthreshold slope, and the best way is to minimize this M value close to 1. And of course, as I told you before, there can be many different ways using relatively low Na value or having higher oxide thickness. That's good, really good, but best way is just to eliminate this silicon depletion capacitance itself. And how can you obtain this kind of zero capacitance? It was related with introduction of our so-called completely depleted substrate. So please note this technology progress. Okay, so then for remaining 15 minutes or 20 minutes, I will try to cover the remaining lecture contents once again. But please note that today's main message is related to this factor M. How can you control this factor M? And I will explain a little bit further about the meaning of this M factor. So in the previous slide shown here, now we understand M is just showing the relative ratio between depletion cap and oxide cap. Then we can visualize in this way. Here, please have a look at this graph, and this is the constellation or situation of our MOS structure. Where can you find your substrate? Your deep substrate is located here. Here we have a substrate. And where can you find your gate material? Then you can find your gate material at here. Here you have a gate. Then where is the interface between oxide and silicon? This is the point for your interface between silicon and silicon dioxide. Of course, please note that this kind of drawing is somewhat simplified. Why we have made a somewhat simplified view, or how can you justify this kind of a simplified diagram? It is possible because since we are restricting ourselves, like gate source voltage is sufficiently lower than threshold voltage. If we have the case where gate voltage is lower than threshold voltage, what does it mean? It means that we don't have any inversion layer inside it. So inversion layer, electrons, does not consume the potential, so we can just treat our substrate as solely given as depletion charge, and this is corresponding to this simple expression as depletion cap here. Please, so this kind of constellation is valid only at this subthreshold region. And in this case, if we have oxide capacitance and depletion capacitance, so why they are connected in a serial way, that is quite obvious. This is a serial connection. Starting from its physical structure, starting from gate, we have to cross our oxide layer, then after that we arrive at the interface, and from interface to deep substrate we also have another depletion capacitance, and they are serially connected, not parallelly. If we have this kind of thing, then overall capacitance of these two serially connected capacitance can be obtained by Cox times CDM divided by Cox plus CDM. So this is just equivalent capacitance of your two serially connected capacitances. Then now let's assume that you have changed your gate voltage by amount of delta VGS. So this delta VGS is the voltage difference across our entire system. So it is corresponding to delta VGS. So when you have a look at this expression, then this expression just describe the amount of positive charge newly additionally collected at this point, and this amount of charge should be also compensated by what? Also here we have the same amount of charge is required. Then how can we have this amount of charge this charge should be equal to also the charge collected by this second depletion charge. I mean that this charge should be equal to what? Only CDM multiplied by this surface potential change, delta phi s. So are you all with me? I'm just showing that if we have two serially connected capacitances, then change between the overall system, potential change in the overall system, and internal change of the intermediate node are related by this way. Then please try to make a comparison between these two components. For example, delta VGS divided by delta phi s. So you can just send this term into the left hand side, then you will have also, yes, they are eliminated to each other, then you will have Cox plus CDM. That will be, when you just calculate the ratio between delta VGS, the overall, the controllable, our external voltage change, and our internal, we cannot directly change the surface potential. Only by changing the gate voltage, we can indirectly change this surface potential, and it is given as just 1 plus CDM over Cox. What is the meaning of this expression? This is nothing but just factor M, and M just shows that the ratio between your controllable parameter, gate voltage, and your desirable parameter, internal quantity, phi s. So what you wanted to have is, well, change 0.1 volt in your gate, then you wanted to just change exactly the same amount of 0.1 in your substrate or the surface potential. So if we have just number 1, yes, then we can say that gate potential change is directly copied into the change over your surface potential. That's good, but unfortunately, since our capacitor, our silicon substrate itself has its own inertia, so oh no, I have my own internal politics, so therefore your additional voltage should be consumed by me a little bit, so there can be certain division between them. So simply speaking, this M factor represents the ability of our gate to control the surface potential. If this number is 1, it means that just gate voltage perfectly control the surface potential. And if this number is not 1, if we have a higher number, for example, let's say that 2 happen to be, let's say that this is a 2, means that only when you increase 0.2 volt of your gate potential, then your surface potential is increased by 0.1 volt. So it just gives you the control efficiency of your system. Well, then why don't we just introduce the other way around, delta VGS and delta phi s. You know, it is not my intention, my invention, so this is just historically this M factor is taken, so it is just given as a ratio between these two quantities in that way. Okay, so anyway, the physical meaning of our M factor is just the control efficiency of our surface potential of our gate potential. So if you can understand, I think that today's lecture delivers its main message. After that, now you can go to the saturation current. So where do we have a saturation current? So please have a look at our IV characteristics shown here. For example, when you have a look at this curve, so according to our previous expression, so now it shows a parabolic behavior. After it reaches its peak value, after that it is just going down. Of course, this going down, this right half of our parabola, inverted parabola, should be neglected. Why we have to neglect this one? Because our starting point, so simpler form of ID itself was obtained from certain expression for our charge densities. At the time, please remember that we have already assumed that we have inversion layer in our system. Also, so simply speaking, beyond this peak point, then now we can say that when we have the drain voltage, which is corresponding to the onset of saturation current, then our approximate expression lose its validity, so we have to just keep it as a constant value. Okay. The final thing we have to cover is subthreshold current. Subthreshold means that simply the gate voltage is lower than threshold voltage. Well, then yes, this is the case. If we further reduce the gate voltage, then we enter into accumulation reason, but practically we don't use accumulation at all. So we can just say that when gate voltage is lower than threshold voltage, then that is corresponding to subthreshold region. Then our previous expression matched to the beyond threshold cannot be used any longer, so we have to come back to our original equation. So please do it together with me. So first of all, when you have a look at this one just shows you the silicon charge. And silicon charge in its exact form, instead of this only two terms, we have more terms like a linear term and exponential minusly so something like a exponential minus phi s over kBTQ. This kind of terms are shown. However, all of these are not very important because they don't have enough magnitude. So we just consider two major terms. One term, this term, is of course related with our depletion charge, and another term, this term is related with inversion charge. Then how can we actually separate it? Of course, in its original form, they are all coupled. Sum of these two contribution is square rooted, so we cannot easily separate it. However, fortunately, when we have substrate case, then we can easily understand. Here we have two terms, and since we have here quite small leading coefficient in subthreshold region, this second term is much lower or smaller than the first term. Then we can make a Taylor expansion of this square root. I mean that it's like this. Here we have a plus delta, and let's say that delta is quite small and even close to 0. Then it can be Taylor expanded by just square root of a, and also we have this leading coefficient and delta. That can be used for our Taylor expansion only up to first order. Of course, we can expand even further, like a square of delta and cube of delta. However, all kinds of these terms can be safely neglected because delta in this case can be regarded sufficiently small. So when you do it, then you can identify QS can be just made of sum of these two terms, and these two terms just identified as, okay, this is corresponding to the depletion charge, and this term is identified as inversion charge related. So you can easily understand this is possible. So simply speaking, now we have good approximate form for our Qi. Our Qi is given as this coefficient and this, seemingly quite complicated, but anyway, basically it is nothing but just exponential phi s adjusted by our electron Fermi potential. So here we have one expression for Qi, and from this Tower equation 3.10 we can just perform the integration of our inversion charge Qi over electron quasi Fermi potential from 0 to the VDS applied drain voltage. Then fortunately this integration can be easily done, because although we have many coefficients, but they are all just numbers, and basically this is nothing but just exponential function of our exponential function of our electron quasi-Fermi potential. So when we did it, then now we have this expression. Please note that this expression is not a general expression, but this expression is valid for our sub-threshold reason. So now we can have this equation. Here I have shown you a red colored term. This red colored term, and it is important dependence on our applied bias. Of course, here we have another term, 1 minus exponential something. However, that is not that important. So please think about this case. When we have VDS equal to 0.1 volt, 0.2 volt, 0.3 volt, 0.4 volt, just to increasing our VDS value. If we are working in our conventional inversion mode, then if we increase our drain voltage twice, 3 times, first of all we expect an increase of our drain current twice, 3 times. However, as you can see here, when you just increase this VDS value, then actually this exponential function quite rapidly approach to just number 0. So beyond a certain level, then entire factor just becomes 1. So it means that in sub-threshold region, ideally your drain current should be independent on your VDS. This is very important. So please understand this one. After that, in the next slide, I just make a conversion from our surface potential into gate voltage using a restricted expression. Then it can be expressed as this form. What is the difference? Previously, we have used the exponential dependence on electrostatic surface potential, but this surface potential is converted into our gate potential. And up to now, I have stressed that the trade ratio or efficiency between gate voltage and surface potential is given as M. So as you can see, starting from our original surface potential dependence, when we convert it to gate potential difference, then we have to introduce the conversion factor, and it is shown here M. Wow. So it means that if M is 1, then our current is sensitively dependent on the gate voltage. However, if this number is 2 or 10, it means that although we have increased our gate voltage at the same time, same amount, however, the increase of gate current will be much more marginal. So, simply speaking, if we have a gate source voltage and ID written as drawn as a semi-logarithmic scale, if we have M equal to 1 case, then we will have a relatively steep behavior. However, unfortunately, if we have higher M values, then our increase will be degraded, and these cases are taken as or regarded as undesirable cases. So we wanted to keep the value of M as close as to unity value number 1. Okay, so the remaining slides can be covered by yourself. So since the time is up, so I would like to summarize our entire semester. So we start from the review of our basic device physics. We spent quite some time, and in my opinion, actually the most important discussion of difference over our previous lecture, junior level microelectronics or semiconductor physics, was the introduction of electron quasi-form potential and hole quasi-form potential, and they are directly related to the applied voltage. So in this course, you should be able to identify your current density in terms of this quasi-Fermi potential. Gradient of quasi-Fermi potential is related with your Jn expression and Jp expression. In my opinion, that is the key point. So this is a long story, so we could not cover in our junior level semiconductor physics or device course, but in this course we spent quite a long time on this concept. Once we understand this concept, quasi-Fermi potential, then we can extend it to our MOS system, and the complete theory on our MOS transistor were built, as you have seen in our previous lectures. Okay, so thank you for your participation during the last 25 lectures, and see you next Monday for our final examination. Thank you.